So in example 7, this kind of looks like something we could handle with our old basic u substitution, and I always want you to try that, so I'm going to try that now. I'm going to let u equal x squared minus 7, because it looks pretty promising. When you look at that, it feels like, hey, this might work. I have my substitution there for dx, and I'll try to kind of scramble this over. We decided, let me clear that, we decided to let, u equal that thing underneath, just because that's your best choice of u for u substitution, the thing inside a composite function. And then I have this follow through for dx, which is du over 2x, but this didn't line up right. I was not successful in getting rid of the x variable. You've actually made it worse. you have x's left over that you can't take outside the integral. That's illegal. So it's still a good idea to try u substitution, to think about it, because on your Unit 3 test, everything's going to be mixed up. And so you want to try something easier than something more challenging, right? So I just wanted to show this to you, that this is not, I don't consider this a failure. If this happens to you on the test, you're just going to come in here and say, nope, I'm going to put a line through it. And I know that that means don't grade that, and then you'll restart, okay? So, but I want to keep this in the back of your mind, that we can still think about things like this. Let's see if I can come in here and cut. Okay, because I'm going to need some space. So because our basic u substitution failed, and it doesn't really look great for integration by parts, I do happen to see, I want you to notice, I see a square root with something squared and a number. And that's going to be your trick. Like that, this is where trig substitution is useful. Okay, so I'm actually kind of diagnosing it by what I see. So I'm going to do this trig substitution, and I'm going to decide what we're going to do. I'm going to look at that and say, okay, I'm going to let u equal x, and I'm going to let a equal the square root of 7. It's okay. It can be ugly like that, right? What's squared gives me 7? Well, the square root of 7. So now I'm putting this together as a trig substitution. So I just like to kind of say, look, I'm not doing a u substitution. I'm putting these two puzzle pieces together. And when I see something like this, where it's the variable of x function squared minus the number, then this is kind of like if you think about your derivatives. This is like an arcsecant, where it was like the variable, a function of x squared minus a number. And that's what your trig substitution is. You're going to let u equal a times the secant of theta. Now for this problem, remember, you said that that u was x, that a was the square root of 7. And I'm going to make that swap. That is my trig substitution. But I don't want to forget about the fact that I'm going to have a follow through here. So I am going to do it. I'm going to take the derivative of both sides of that expression, so I'm ready to go when I need it. So I will come at this integral, and I'm going to rework it. So I have this giant radical up there. Now in place of x, remember x is the square root of 7 secant theta. So I'm going to make that idea there. So let's put that in there. Square root of 7 secant theta. All of that's squared, right? Then I have a minus 7. In the denominator, I have 2 times x. Got it. And in place of dx, what do I have? This whole statement over here. The square root of 7 times secant theta, tangent theta, d theta. So trig substitution always looks a whole lot worse before it ever looks better. So I am going to work on that radical. The whole point is you want to eliminate the radical. So all of your attention should really be up here. Like, what can I do to get that to work out? Okay. What I can do from here is do that. So let's play around with that. I have, if I square the square root of 7, that's 7. Then I'd have secant squared, and then that minus 7 is kind of hanging out. What I am going to notice right here, if you see it, this root 7 can cancel with that root 7, and the secants can cancel as well. So why not make this a little bit friendlier? If things start to cancel, let's maximize that. So let me keep working on that radical in the numerator, because what I can do inside that radical is I can say, I see that there are 7s on both of those, factor the 7 out, but you're still inside the radical. And here is the reason why they chose you to use this particular trig function as a substitution, because what I see here, secant squared minus 1, that is a Pythagorean identity. I can replace that with tan squared. So what does that mean? Well, that numerator is then the square root of 7 times tangent all over 2, and then you have this extra tangent d theta off to the side. So that means my integral has just transformed. I can take the numbers out, the square root of 7 divided by 2. I can pull that stuff out. And I now am charged with integrating tan squared theta, which is not a basic integral. However, I can do it. Back when we talked about these trig integrals, if you had the tangent function and the power was even and positive, switch to secant and see what happens. So what does that mean? It means I'm going to use that Pythagorean identity again and replace it. This is legal. I'm just making, a swap for tan squared like this. Now, the reason I want it like this is because, I know what the antiderivative of secant squared is, right? That's tangent. And I know what the antiderivative of 1 is, d theta. That's just theta. So you're good. That's it. You can integrate term by term, right? So integral of secant squared is tangent. That's a basic rule you have to know. The integral of 1 d theta is theta. This is great. That is your answer, but that is not your final answer because your integral had an x variable in it. So I need to somehow undo the thetas in here. Let's write the equivalent algebraic statement for tan theta. So let's go back up to what our substitution was. X equals the square root of 7 times secant theta. Let's solve that for secant. That would mean x over the square root of 7 equals secant. All right, I'm just kind of maneuvering that around a little bit. Let's create a triangle where theta actually has its secant to be x over the square root of 7. Now secant is hypotenuse over adjacent. And so what I need to do to answer what's the tangent? I need the opposite side. So just use your Pythagorean theorem, right? Hypotenuse squared equals 1 leg squared plus that opposite side squared. So it turns out, once again, that opposite side happens to be familiar. That's what you replaced in the original integrand. That happens a lot. Okay. So now that I have that full thing, worked out, then let's replace it. So square root of 7 over 2. Tangent is opposite over adjacent. Now, theta, let's think. If secant theta equals x over root 7, remember that trick, I'm just going to arc secant both sides. So that would mean theta equals the arc secant of x over the square root of 7. Okay, so I'm just going to move that root 7 over 2. I'm just going to distribute it through. I mean, this would be fine, but I might as well just kind of carry it through. It's kind of nice when you carry it through here that the root 7s cancel, so it looks a little bit friendlier, I suppose. And then I'll carry it through here, and it's just a coefficient. I think it looks better like that. So there is my antiderivative for problem number 7. Okay. So they're using these trig functions. They're setting you up so that the Pythagorean identities work amazing, so that you can get rid of the radical. Every single time you're going to eliminate the radical and replace it with that Pythagorean identity. Okay. So let's take a look at our last one, essentially. I know that there are 2 more problems left, but this is really the last one. Okay, so this one, I wanted to set up something where, this is not a U substitution problem. You can kind of imagine that in your head, that You could let u equal 4x squared plus 1, but that's not going to work for a basic u sub. I also I'm not going to even think about integration by parts, just because what I do see is I see a radical with functions underneath where I have a variable function of x quantity squared and a number. Now they're both being added here, which if you think about the derivative of arctan, that's the one that had the plus sign in the middle. And so that's what I'm going to do with my trig substitution here. So I am going to handle this as a trig substitution. I'm going to let u equal 2x, because 2x quantity squared would give me 4x squared, and I'm going to let a equal 1. And I'm putting these together as a trig substitution. So I'm going to use the substitution that u equals a tan theta. So here that means 2x equals 1 tan theta. And I'm going to hang on to that. Right? I guess you don't really need to write the 1, but right here, right before I forget, I'm going to actually take the derivative of each side so that I don't forget about it. You always need to follow through, and so it's an important thing to do. I usually do it right away. And I'll even solve it for dx, right? Because that's the issue. The reason I'm using it is I need to get rid of that dx. So I'm going to write 1/2 secant squared theta d theta. That's what dx is. All right, so let me go to my integral and rewrite this. You are transferring this integral in terms of the x variable into a bunch of trig functions. So what do I have here? I have 2x quantity squared plus 1 quantity squared, and then I have a dx. Now, anywhere I have a 2x, that is now going to become tangent. And in place of dx, I'm writing 1/2 secant squared theta d theta. So this integral looks a whole lot worse because it looked friendlier here, and now it has all these trig functions. But the reason I'm doing this is to use some of those trig identities. I'm going to whittle this down. Under that radical, you have tan squared plus 1. And tan squared plus 1 is the same thing as secant squared. That's why they told you to use that particular trig function in your substitution, because now, well, the square root of secant squared is just secant. And I can now look at this integral and say, like, oh, I can take that 1/2, let's throw that out. That's just a number, that's legal. Secant squared over secant is just secant. And this is actually on your formula sheet. You have an integration rule for integrating secant all by itself. It happens to be, well, I'm going to write the 1/2 because that's just kind of there, the natural log of the absolute value of secant theta plus tan theta, make those absolute values super obnoxious, and then a plus c. So you've got an answer. It's not the right form, but it's really good. I mean, it is equivalent, but I need to represent my answer in terms of x. I mean, if that's the integral I was given, my answer should have x's in it. So let's actually transfer it over. I need to know what secant theta is in terms of x and tan theta, what that is in terms of x. So I'm going to go back up here and just rework this. That means 2x over 1 is tan theta. I'm going to draw a triangle that has theta in it where the tangent really is 2x over 1. And if I'm looking for secant, I need to know what that hypotenuse is. So remember, just Pythagorean theorem, hypotenuse squared equals one leg squared plus the other leg squared. And so you kind of see that original statement kind of come flying back at you. It always looks familiar, that missing side. So I'm going to put that on my image. And now I'm just going to translate back. So no weird identities here. The secant is just hypotenuse over adjacent. And the tangent is opposite over adjacent. And so we don't really need the over ones here, of course. It makes it look more complicated. And there is no logarithm property to handle this. There's nothing you can do with a plus sign in the middle here. So I'm just making the absolute value look really obnoxious here. But that is a good antiderivative for this problem. Okay, you were given an integral in terms of x, and now your answer is in terms of x. Now, if you see on your notes, there is one last question, and this is where I sort of circle the wagon here a little bit, and just remind you, like, you need to be totally set on every kind of way that we have talked about integrals, and I don't see a radical here, so I don't think you need trig substitution. I want you to think back into what kind of integral this is. This was probably on your Unit 1 test. It is not a U substitution. However, this will work. Kind of feels like a trig substitution. I'm going to say that U is 2x. I'm going to say that A is 1. And I'm going to translate this integral just using those little pieces of information. Now remember, I have a follow-through, of course, anytime I'm doing something like this. This is your arctan. All I have to do is come in here and make the appropriate swap for dx. dx is du over 2. So basic U substitution fails, but I don't want you to just go with trig substitution just because you see a bunch of stuff squared. There's no radical. This is just a basic arctan antiderivative. So I'm going to rewrite it. I'm going to take that 1/2 and pull it outside the integral. You can do that. It's just a coefficient. And then remember, like, well, what is this? This is going to be 1 over A arctan U over A plus C. So that would be 1/2, 1 over 1 arctan of 2x over 1. So not everything has to be a trig substitution. And I just want to remind you about all the awesome stuff you can do without it. So trig substitution is just one extra method added to your list of basic integrals, trig integrals, U substitution, integration by parts. And so if all of those other things fail and I end up with a radical that I want to eliminate, then trig substitution is a good idea. But I don't want you to forget all your other skills. I want you to recognize something like this as just being the antiderivative for arctan, okay, or the derivative of arctan. Sliding back up to the first page, hopefully I'm not making you motion sickness here. Like number 2, we started with that, right? That we should recognize that that is, in and of itself, this is the derivative of arctan. So I don't want you to forget about those old skills that we talked about.